All right. Welcome everybody to today's Dots. We have an all-European cast for today. So first off, I'm happy to introduce Axel Parmentier. Axel is a researcher at the Ecole des Ponts ParisTech, where he holds a research chair in OR and machine learning in partnership with Air France. Axel has done lots of work related to airline operations using different machine learning and operations research techniques like column generation, integer programming to solve these kinds of problems. And for his PhD work, he's received the 2016 Young Researcher Award of the French Society of Operations Research and a 2017 PhD award for the best PhD in France in math with interactions in industry. And so today he's gonna tell us about some of his recent work on the intersection of machine learning and integer programming. So Axel, please go ahead.
Thank you, Elias, and thank you, Alexander and Elias, for inviting me at this talk. And it's a pleasure to talk about some work I have done about how to use machine learning for operations research. And first, I apologize if at one moment you hear a big noise. It's because my neighbor has had the great idea of drilling the wall 10 minutes ago. So now back to math. What I'm interested in today, it's about the machine learning techniques that you can use to speed up operations research problems. So let us consider a generic operations research problem where what we want to do is to minimize a function f of x on a set of feasible solution x that belongs to big X. What here, this is not so common. I introduce gamma. Gamma denotes the instance, because as we are going to do machine learning for operations research, we will consider many instances of the same operations research problem simultaneously. So both in the objective function and in the feasible set, I will recall the instance that we are going to solve. And most operations research for machine learning methods proceed in that way. First, you have an instance and you use a machine learning predictor, phi theta, to extract relevant information from the instance gamma. Then, in the second part, you use an algorithm that I denote A to exploit this information to build an interesting solution X of the optimization problem you are looking at. And so the learning part is to find the best theta in a family of predictors, such that the algorithm, based on the information extracted by phi theta, performs as well as possible. This is done offline and can take a lot of time. The second part, the algorithm A, is the prediction or inference task. Then it's just computing phi theta and running algorithm A. This is done online and it must go very fast. So several different schemes can be used using this general idea. The first one would be end-to-end learning. In that case, there is some growing literature on the topic, and it has been applied mainly to the traveling salesman problem. Phi theta is an advanced machine learning predictor, typically a deep learning network, extract information that is then used by a greedy algorithm to reconstruct a solution of the traveling salesman problem, for instance. And up to now, it does not work so well in the sense that it does not match the performance, the state-of-the-art, the performance of state-of-the-art operation research algorithms. And one of the reasons why I think this happened is because, well, when you use a greedy algorithm to reconstruct the solution, you do not exploit the structure of the problem. And what makes operations research algorithm work most of the time is to exploit the structure of the problem. Another way of using this paradigm is to automatically tune state-of-the-art algorithms. Typically, here you would have an advanced solver, for instance, Cplex or Groby, and you use an ML predictor to extract an interesting parametrization. And this works very well. And one of the reasons why it works very well, it's just that, the advanced solver exploits the structure. But there are several contributions along that line. But one of the situation I want to address today is not exactly that one. It's I just want to do more than parameterizing good algorithms. I want to be able to have good heuristics for problems that would be hard problems that we do not know how to solve in practice. And I'd like to ask you the question that's if some of you have been in the following situation. You are considering an operations research problem. It comes from it's as a practitioner, and it comes from the industry. And your problem is just like one of the well-known operations research problems, but there is this additional constraint, or there is this little change in the objective that makes everything collapse, and you can't use the good theory that exists on the classic operations research. And what I want to do is to use machine learning to address that situation and be able to use the good theory that has been constructing for a long time in operations research on my variant of the problem. And so what I will provide is a generic methodology to build efficient heuristics in that case. How does it work? Well, we have a hard problem of interest that I will put H to denote that hard problem of interest, and we want to minimize a function that might be complicated on a set. And it is a variant of a well-solved problem that we know well in operations research. For instance, a shortest path problem, or a flow problem, or a traveling salesman problem, on which we have very good algorithms. And the idea is we want to exploit the good algorithms we have on the easy problem to solve instances of the hard problem. So how we will do that? First, we will take an instance of the hard problem, and we will use machine learning to turn it into an instance of the easy problem. And then we will use the good algorithm we have for the easy problem to solve that instance of the easy problem. And finally, reconstruct a solution of the hard problem from the solution we have computed of the easy problem. So here what we want to do is to learn the best theta so that we get the best possible approximation of an instance of the hard problem by an instance of the easy problem. So this raises several questions, and the main one is how to build and learn such a phi theta that will turn an instance of the hard problem into an instance of the easy problem. And we propose a structural learning approach that you can use when the easy problem is the usual shortest path problem on an acyclic digraph, or a minimum cost flow problem on an acyclic digraph. And and the approach we will use just require one thing. It's an algorithm for the hard problem that can solve small instances. And we will use it to build a database from which we will learn phi theta. So now let's go to the problem we are considering, and the hard problem we will approximate by an easier one. So this hard problem is a stochastic vehicle scheduling problem. Suppose that you have a set of tasks, V1, V2, up to Vn, that you have to cover with vehicles. And you want to build the sequences of tasks that will be covered by each vehicle. So here, for instance, we have 3 vehicles, the red one, the blue one, and the purple one. And what we want to do, we have the set of paths in the acyclic digraph. That means that maps the sequences that can be operated. And what we want to do, we have a cost for each path, and we want to find a partition of the tasks into paths so that each path is covered by exactly one path. So an application of that, it's the reason why I've studied that problem, it comes from an application at Air France and in airlines in general, that is the aircraft routing problem with delay. So here the tasks are flights, And what you do are what you build are the sequences of flights that are operated by an airplane. And what typically happens when you have this kind of problem, it's that, well, if the flight V1 is delayed, then the red plane will arrive late at the beginning of flight V4, and the delay of V1 will propagate to V4. Practically, we have some slack between the two flights, and if the delay of V1 is bigger than the slack, then the delay will propagate. So the cost we will have for our rotations will be a cost of having an airplane plus the expectation of the propagated delay. And this expectation of the propagated delay makes the problem very complicated, because to be interesting, you have to have many scenarios. And due to this slack problem here, it's very nonlinear. And so how will we approximate that problem? The problem we want to approximate it's, well, if we could replace this nonlinear cost of paths by a gentle cost that nicely decomposes along the arcs of our path, what we obtain is a flow problem. Actually, we can solve it using this flow formulation, and we can solve it even with linear programming, and it's super easy to solve that problem. So what we will use machine learning for is to transform the parameters of the distribution of delay to based on that, estimate a cost that we will C hat A that we will put on each arc, so that C hat P gives you the path of minimum C hat P is a good path in terms of propagation of delay, and we solve that using a MIP solver. So another approach we will use is, well, the generic method to solve this kind of problem when the cost is nonlinear is by column generation. And what we obtain in that column generation using these master problem formulations, where we have an exponential number of variables that are linked to the paths, we obtain a pricing subproblem where we seek the most interesting path to generate. And these pricing subproblems happen to be stochastic in our case, because in the cost CP here, the propagated delay appears. And this makes it a very complicated problem to solve. And so the other applications we will do, it's instead of approximating the master problem, we will approximate the hard pricing subproblem by a usual shortest path problem that is very easy to solve, and embed that in a column generation, the heuristic column generation. The idea being, in the column generation algorithms, you need to generate columns with negative reduced cost, but if you don't solve the pricing subproblem to optimality, that's not such a big problem. Before going into the details of how I construct these approximations C hat A that enables to map the hard problem to the easy problem, I'll give some numerical results obtained on these problems. So the database I use is the following. I use instances with between 50 and 5,000 tasks, between 50 and 5,000 flights when it's the airline application. And in terms of scenarios for delay, I use between 50 and 1,000 scenarios. On my training set, I must be able to solve to optimality the column generation. And so I just have small instances with 50 tasks. So this makes 50 instances in my training set, because I have 10 instances of size 50, 10 of size with 100 scenarios, etc., etc. For the validation set and the test set, I have much larger instances, and I will run on them the exact column generation that enables to build my database, and then the heuristics I obtain by approximating my hard problem by an easy problem. And so I used my heuristic column generation where I approximate the pricing subproblem, the flow MIP where I approximate the master problem directly by a flow problem, and as benchmark, I use a local search and a taboo search because this kind of meta heuristics are typically excels on this kind of problems where finding an easy solution, finding a feasible solution is easy, but finding a good solution is hard. And so let's go to the numerical results. So here I give numerical results. Here you have the numerical results are averaged on the test set instances with given number of size, the number of tasks, and for the different algorithms. And what we can see there is that, well, first, of course, the flow MIP heuristic will be super fast. Why? Because I just solve a linear program that is not so big. And so it can find solution very fast. You have the CPU time, even on very large instances. Second, and more interestingly, the solutions computing behaves well, because as we have learned our predictors only on instances with 50 tasks, what we can ask ourselves, will it work on instances with 5,000 tasks? And to see that, instead of giving the value, just the value of the solution returned, I return the average cost of the solution divided, the cost of the solution divided by the number of tasks. The idea being, the larger the instances, the more flexibility you have to build the sequences of tasks, and so the cheaper it becomes to find a good solution. So it's very easy to build a heuristic that can have an average cost by task that is similar to the one you have on the small instances. You just have to take your big instances, split it in many small instances, solve them using an exact solver, and you will get a solution of the full problem that will have the an average cost by task that is similar to the one you obtain on small instances. What is much harder, and we can see it here, it's that here on large instances, we are able to obtain an average cost by task that is much smaller than the one we could have on small instances. And so that's what says that our machine learning based heuristic works well. It's well on huge tasks. It can solve fast, huge instances and find good solutions for this one. Of course, not optimal. And actually, the reason why I studied that problem initially is that because at Air France, we are interested in solving that problem online. Why? Because when some delay happens, you want to reconstruct the sequence of flight legs operated by your airplane so as not to propagate the delay. And as you use it online, you want to be able to find a good solution of the problem on instances with around 2,000 to 5,000 tasks in at most 2 to 3 minutes. And using an exact solver, we could up to now have only a solution have after 1 hour optimal solution. Yes, on instances with 50 tasks, and on such big instances, we could do nothing. So for the practical applications, we are super happy to use this flow MIP heuristic. If now, if you go to the heuristic generation, well, it's find even better solutions that are better than the one found by the classical meta-heuristics. Well, I couldn't run it on the large instances for memory reasons. The reason why this works quite well can be seen there. On this figure, what is depicted is the reduced cost found by solving the approximation of the pricing subproblem by a usual shortest path problem. And what we can see is on the test set, you have in blue the optimal solution, and in yellow the one that is found by the approximate pricer. And so, of course, it does not find the optimal column to add in the column generation, but it finds a good one, and that's the reason why it works very well. If we zoom on the last iterations, what we can see is that during the last 10% of iterations, we are not able to find any negative reduced cost column, and so the algorithm stops before the end, and that's the reason why we do not have optimal solution. This is on an instance of a different size from the one in the training set. It works slightly worse, but it still works. So now I want to go quickly on the second part of the talk. It's about how did we do to approximate the hard problem by the easy problem. And for that, we use a structural learning methodology. The idea is that here we want to be able to approximate an arbitrary path problem by a shortest path problem. So we will take an instance of the arbitrary path problem, turn it into an instance of the usual shortest path problem, solve it, and get an instance of a solution of our hard problem. The way we do that is we define a feature mapping that takes from the set of arcs and the instance and takes some general information on the instance that will extract information about the arc. And what we will, the family of approximation we will look is that one. It's, well, the cost of the shortest path will just be the sum on its arc of, well, the approximated cost of an arc that is just taken as a linear combination of the features. And what we want to find is the theta such that this linear combination enables to approximate well the cost of an arc. Just to give you an idea of the features we use there, since we are just what we are looking at is the propagation of delay, to an arc corresponds to flights, and what we just look at is the slack between the arrival of the first flight and the departure of the second flight. And we take the quantiles of that distribution for the different scenarios. And we just use 20 quantiles about distribution, and that's what we use to get the results we had. And the way we use to learn the best theta is just to go to formulate it as a structural learning problem. A structured learning problem, what you want to learn is a function y as f of x, but y typically belongs to a combinatorially large set. So instead of you looking at the function f, your function f will just give you the argmin of a function g theta of x, y. And practically, what you take as g theta is just a linear combination of features. There is a whole theory about structural learning to learn theta in that setting. What we figured out in that work is that we could use this theory in our case. In that case, well, this will be, so the inference problem in structural learning will just be our easy problem. And the easy problem, it's just a shortest path problem. And so we will use structural learning techniques to learn a theta that approximates well this argmin with this simpler one. And just how do we learn that theta? Well, from an IID, we're supposed to have an IID sample where we have the instances and the optimal solution, and we want to choose theta. How do we do that? In fact, we will embed the set of paths with a distribution where the probability of a path, a solution, will be proportional, inversely proportional to its cost. So that under the distribution that comes from theta, well, the most probable paths will be the one that have the smallest cost. And using that, we'll just search the theta that maximizes the likelihood under of our observations in our training sets. And so this way we could recast our problem of approximating a hard problem by an easy one as a maximum likelihood problem, just by turning an instance of the easy problem into a distribution. And then we can use the classical theory about maximum likelihood estimation. We just introduce we see that the regularized log likelihood is a smooth convex function with a gradient for which we have an explicit formula, and we will just use a BFGS algorithm to optimize that, to minimize that regularized likelihood. The only difficulty there is that we have to compute L of theta and the gradient of L. And in L of theta, as it's an expectation there, where intervenes, well, something complicated, that is a sum on all the paths. So this computing the objective and the gradients looks very complicated. But in practice, what we observed is that we could compute it in linear time using a sophomore version of the usual dynamic programming algorithm. To make it short, if you write everything, you will see that the partition function satisfies this equation, and everyone in operations research knows this equation. If you just change the sum by a max and the multiplication by a plus, this is just the dynamic programming equation. And so what we have done is, how do we solve our learning problem? That's the magic of the thing. We just have to, instead of using the usual dynamic programming algorithm, we use the dynamic programming algorithm, where instead of the max plus algebra, we use the classical plus multiply algebra. And we can do exactly the same thing for the gradients. And so to summarize what we do next, we take the instance of the stochastic vehicle scheduling problem. We run an exact column generation on each of them. We store all the pricing subproblem instances we encounter along the column generation. This builds our training data set as a shortest path problem. And we use the algorithm I have just presented to learn the theta that will approximate well the pricing subproblem by a usual shortest path problem. And in fact, we can use the theta that we have learned there also to approximate the master problem instances by a flow problem. And so the learning results we have, well, it took a long time to generate the database, 28 days, but since what we have in the end to learn the problem is just a convex problem where we have dynamic programming to compute gradient and objective functions, it takes less than a minute to run the algorithm. And here are some information on how we choose the regularization and hyperparameters. Last things, well, still our learning algorithms depends on what we use in our training set. And what we have seen in our validation set is that if we used two small instances, so here the training sets contain much more instances, but very small ones, it performs slightly less well than if we use a smaller training set with larger instances. And in conclusion, what we propose is a machine learning for operation research paradigm that enables to approximate complicated variants of a problem by a simple one. In our case, a complicated stochastic path problem by a usual shortest path problem, or a master problem of a column generation by a flow problem. And how did we do that? We introduced a maximum likelihood approach to that use structured learning techniques to learn the approximation of the hard problem by the easy one. Thank you very much.
Hey, thanks a lot, Axel. So I'm sure many people, including myself, have questions, but given that we've hit 2:30, I would ask you to just defer them until 3 p.m. After Dolores' talk, and you'll be able to chat in a chat room with Axel and ask him any questions. Okay. So Alex, go ahead.
Yeah, thank you very much, Axel.